Osteoporosis is a condition which means that our bone strength weakens with age, and about 500,000 people every year in the UK will sustain what's called an osteoporotic fragility fracture, and it costs the NHS about £3.5 billion per year. The change in structure with age is very clearly seen on this image here, which is from a high-resolution computed tomography scan. On the left we've got a young healthy individual, on the right we've got a more older frail individual, and you can see the loss of bone structure that occurs with age. In addition to knowing about bone, however, I need to know about the whole musculoskeletal system. I need to know about muscle strength, I need to know about reaction times, and that's why we need to be able to combine this information together to tell me who's at most risk of fracture in the future and allow us to intervene.
So in bone you have two types of cells, osteoclast, which removes old bone, and osteoblast, which makes new bone. And the process of making new bone and removing old bone is called bone remodeling. In healthy bone, osteoclast remove old bone and osteoblasts make new bone at more or less the same rate, which means that the process is balanced. However, with age, osteoclasts become more active, more numerous, and they remove more bone, whereas osteoblasts, because of age, are less able to produce new bone, and therefore there is an imbalance. More bone is removed and the bone becomes thinner and more fragile and more likely to fracture. At present, treatment rebalance bone remodeling, and they work for some patients but not for others. So what we really want to know is what are the patients that respond to the treatment, and those that don't respond, why they don't. And in particular, we want to look at the effect of muscle. We know that muscle change with age and therefore may have an impact on bone remodeling.
Here at the Insignio Institute, the musculoskeletal group, we do a range of different modelings. We can use a high-resolution peripheral CT scan, typically of a radius of tibia of a patient. We can create a virtual model of that scan, and we can apply compression, for example, to that piece of tissue. And we can study how any cellular or tissue level changes would affect the bone mechanical properties for that particular patient. Another good example of the type of modeling we do, which is on the organ level, and that typically involves, for example, a whole bone such as the femur showing here. This one is shown of a normal patient, and this one here is an osteoporotic patient. So on these virtual computer models, we can apply a range of different loading conditions in different directions to simulate, for example, daily physical activities such as climbing stairs or an accident such as a fall. And the computer models will tell us a prediction of how strong the bone is and the likelihood of a fracture for that particular patient in the future. So here we can see a patient walking, and this is a typical whole body dynamics analysis that we do here. You can see the green arrow indicating the ground reaction force to this patient, and the strings are showing the muscle, blue being inactivated and red being a muscle being activated. So this type of body level analysis is very useful in terms of informing the amount of force we need to apply to our models. And also it tells us information about the motor neural control of these skeletal muscles. So in the future, the modeling work is very much focused on combining the cellular level activities with the bone model and skeletal muscle model we developed to try to make the model more accurate and efficient to run.
In the clinic, I'm interested in doing the best for the patient sitting in front of me. To do that, I need to know as much information about them as possible. So ideally, I would have a personalised computer model for that patient that would tell me not just their bone strength today, but would estimate what their bone strength would be like in 5 to 10 years' time. And not just their bone strength, but their muscle strength, their ability to move. And to put all that together to allow me as a doctor to decide what's the best intervention that I can target to decrease that individual's risk of fracture.